Okay guys, chapter 19 is acids and bases. We start off the chapter talking about just the properties of acids and bases. So your book goes through them. It doesn't really have them bolded or put in a list like this, but I created the list for you. So these are the general properties of acids. Okay, they are sour if you taste them. They react with metals. They will turn blue litmus paper pink. They are electrolytes, which means they conduct electricity when they're in solution. And this is probably the most important one down at the bottom. The concentration of H plus in the solution is greater than the concentration of OH minus. Okay? The bases are pretty much the exact opposite of acids, which we will talk about why they're opposites a little bit later in the unit. But they are bitter instead of sour. They are also very, very slippery in feel. So if you guys remember the last lab we did when we were cleaning it up, things started to get very, very, very slippery. And that's because we gave you sodium hydroxide was your chemical that we did for the heat of solution. Bases do not react with metal. So this is why if you have drain cleaner at your house, you read the side of it, it's going to be calcium hydroxide or aluminum hydroxide, or it's going to be some sort of base, because the base will react with the hair and the skin and all the gunk in your pipes, and it'll leave the metal alone. Okay? It'll turn red to litmus paper blue. It is also an electrolyte. So again, remember, electrolytes just conduct electricity when they're in liquid form. And then this one is the opposite of that, which is the hydroxide concentration is greater than H plus. So you need to know those properties, because you'll get questions like, you discover a substance, and when you put it in water, you notice that it conducts electricity, and it's sour to the taste. You have to know that that chemical is now an acid. Okay? The next section gets us to models for acids and bases. Okay? And what I'm going to do here is I will teach you a third one that you'll need to know for later chemistry classes. A lot of you guys are going to be taking U of U Chem next year. Your book does talk about Arrhenius acids and Bronsted-Lowry acids. It doesn't really talk about Lewis. So I'm going to just briefly explain what a Lewis is here in a minute. But Arrhenius is the ones that we've been learning all year long. So we said if it starts with H, which means it's H plus, then it's an acid. And if it has hydroxide in it, then it's a base. So the Arrhenius definition of an acid is something that contains H plus ions, and the definition of a base is something that contains hydroxides. So an example of that would be hydrochloric acid is an Arrhenius acid, and potassium hydroxide is an Arrhenius base, and that double replacement would make potassium chloride and water. And just like when we were balancing equations earlier in the year, I reminded you guys, anytime you see an acid or a base, rewrite water as HOH. It makes everything way, way easier to balance and to keep track of what's going on. Okay? The next definition is the Bronsted-Lowry acids and bases. And its definition is a little bit different than Arrhenius. So Arrhenius' model can explain anything that fits into our old system. So it can handle about 90% of the acids that you would want to run into or deal with on a regular basis. But there are some chemicals, like ammonia, which we use to clean our windows, that are only acids or bases because they react with the water. And so the Bronsted-Lowry definition says that an acid is anything that will donate an H to someone else, and a base is someone who will accept NH. And so this is the example of that. Ammonia, when you mix it with water, the water will donate NH plus to create ammonium, and the water is now left as a hydroxide. And it's this hydroxide that cleans your windows. So everyone knows you put window cleaner has ammonia in it. It is because the ammonia will actually break apart the water that's with it and create a base. And that base is what will get all the gunk off of your windows. And then Lewis, this is the one your book doesn't talk about, but I'm going to just mention it. It's basically the opposite of Bronsted-Lowry, but it's the same because if you're donating a hydrogen to someone else, then you are keeping your electrons. So even though these two look like they're the opposite, they're really the same. Okay, so a Lewis acid is someone who accepts electrons. And a Lewis base is someone who donates electrons. So here's an example. We have PCl3, which has that lone pair of electrons there from back in chapter 8 when we had to draw these. And this is boron trifluoride. This substance right here is donating electrons to the boron. So this is the Lewis base. The BF3 is the Lewis acid. And this is the result. Okay? If we were to go through and assign charges, the phosphorus just lost a charge, which is why it donated the electrons, and the boron gained a charge, which is why it accepted the electrons. Okay? Within the Bronsted-Lowry definition, there's this vocabulary word right here, amphoteric. Water is our poster child for amphoteric. Just like an amphibian can live on land and water, the amp in front of it tells you that it can do both. And so water is an amphoteric substance that can both accept hydrogens to become hydronium, or it can donate hydrogens to become hydroxide. So it can behave as both a Lewis base and a Lewis acid. Sorry, Bronsted-Lowry, not Lewis. Okay, so it can behave as a Bronsted-Lowry acid or a Bronsted-Lowry base. Okay? So now that we know what acids and bases are, we now need to know what's a monoprotic versus polyprotic, and what's a monohydroxic versus a polyhydroxic substance. So here are 3 examples of acids, and these are all Arrhenius acids because they start with H and they contain H+. But this substance, if it splits into water, only has one H+ that it can donate, and so it's mono. And if you remember what we learned way back when about hydrogen, hydrogen only has one proton and one electron. So if it's an H+, you lose the electron, so an H+ is really just a proton. So this is called monoprotic. And sulfuric acid has 2 hydrogens it can donate, so this is diprotic. And H3PO4 phosphoric is triprotic. Okay? This becomes really, really important when we get to section 3 and we do the math. Because if it's triprotic, you have to multiply by 3 every time you have math that involves the hydrogens. If it's diprotic, you have to times by 2. So this is how we classify the acids. The bases, it's the same way. Okay? So this sodium hydroxide is monohydroxic. Calcium hydroxide is dihydroxic. And aluminum hydroxide is trihydroxic. Same reason why these are monoditri is the same reason why these ones are monoditri as well. And again, this idea really matters when we get into the math. Right now we're not doing the math. So you just have to make sure poly is anything with more than one. Okay? There's di, tri, tetra, penta. There's all kinds of different levels of polyprotic. We'll only go up to 3 in this class. Okay? The next section, strengths of acids and bases. Okay? In chemistry, the word strong always means completely ionizes. So if it's a strong acid, it must be an acid that completely splits when you put it into water. If it's a strong base, it must be a base that completely splits when you put it into water. Okay? The word weak means partially ionizes. Okay? Where that matters is when we start doing the math. If you put 1 mole of a strong acid in water, all of that 1 mole converts into H pluses. But if you put a weak acid into water, only a piece of that 1 mole will split. Okay, so the math is actually harder for the weak than it is for the strong. For this class, you just have to know the 6 strong acids and strong bases that your book gave you in the tables, but I have rewritten them here. Okay? The 6 strong acids you have to know are strong by just seeing them are hydrochloric, hydrobromic, hydroiodic, chloric, nitric, and sulfuric acids. So those are your 6 strong acids that you have to know them. Okay? And then the 6 bases are sodium, potassium, rubidium, cesium, calcium, and barium hydroxides. And if you remember when we watched the video from my website, the one girl sang a song about acids and bases. If you really want to know all of the strong bases, if you look on your periodic table, okay, there's the alkali and the alkaline earth metals. If you really want to know all the strong bases, they form a B on the periodic table. It's all the alkalis, and then it's calcium, strontium, and barium. So that's one way that teachers get kids to remember the strong acids and strong bases. I only need you to know these 6 for my class, but in future classes you might need to memorize all of the strong bases, which would be everything in that section of the periodic table. Okay? And the last thing in section 2 is the K's for acids and bases. So I'm going to shrink this over here so we can see it. Okay? So from last chapter we learned how to come up with a KEQ. Okay? Your book will always throw water in here as a reactant for these, but because water is an L, just like we learned last chapter, you never have to include it in your KEQ, so I left it off. So really what we're doing is we're keeping track of a KEQ, and now this looks like a solubility product, which means it's really a KSP. Okay? But how would we do this? If it was a strong acid, we would assume there's none of the reactants. So we would just say the K would be H times A. But because most of the acids in the world are weak, we are going to have to keep track of all 3 species. So what happens is, it's the H plus times the anion divided by the dissolved acid that has not split. Notice how it's AQ. Because this is such a special K value, we give it its own symbol. And Ka is always the H plus concentration times the anion concentration divided by the weak acid concentration. Okay? For bases, it's the same way. So you have a base that's aqueous. Your book will put water in there, which we won't. So what you end up getting is you have the conjugate acid, which has to have a positive charge, times the hydroxide concentration divided by the concentration of the original base. And again, this can be any base. So that's why these are just generic formulas. But again, it's such a special one that we give it its own symbol, Kb, which is always the concentration of the conjugate acid times the concentration of the OH divided by the concentration of the base. And sections 1 and 2 have a lot of vocabulary and a lot of stuff you gotta have sorted out before you try to do the math. In sections 3 and 4, it's all the math that goes with these concepts. So make sure before you try to do sections 3 and 4, you really have this ironed out. Because when we're going to do the first batch of problems in section 3, we're just going to quickly learn how to calculate H plus, or we're going to quickly calculate how to know what OH is, and then you're going to have to use the fact that this is your normal equation to figure out the other two. So the math will go quick as long as you understand where the math came from.